What's up, everyone? This is LeetCode 155 min stack. So we have to design a stack that supports push, pop, top, and retrieving the minimum element in constant time. So we have to implement this class here, right? The constructor will initialize the stack object, and then this push method will push the element val onto the stack. This method pop will remove the element on top of the stack, and then this method top will get the element at the top of the stack, and then this getMin will retrieve the minimum element in the stack. Now the issue is, like, these functions here are just like normal functions or not functions, these methods are like normal methods you might expect when you're implementing a stack class, right? Now the issue is, how do you implement a stack class such that, like, you can actually keep track of the minimum, right? And the thing is, you really can't do it in O of 1 time complexity using one stack. So you actually have to use two stacks, and that makes it way easier, okay? So that's kind of the trick of this problem. And I'll show you how we're going to do that, okay? So we're going to maintain two stacks, okay? A minimum stack, and then another one we'll just call stack, okay? So let's try inserting an element, right? Let's handle this pushing here. In this constructor, this is where we initialize both of these, by the way, okay? And then for this push, like, let's say we're adding something onto the stack, this 2, and we'll add this 2, right? Because it's empty, so we can add this 2 without any worries. So this will be the new minimum element, right? And here is the element we just added, right? Now let's say we want to add something like a 4, okay? Well, the issue now is that this minimum stack keeps track of the minimum value, right? As we update our stack, right? So if we add a 4, well, is 4 less than 2? No, it's not, right? So if we add this 4 here, we'll have problems, because when we get min, which in get min, really, we're just taking from the top of the min stack. Well, if we check the top of the min stack, we'll get 4. And we'll get, oh, our min is 4. But it's not 4. It should be 2, right? So the way we're going to do this is, when we add a number, like, let's say 4, we're going to check, is this number that we added to stack, right? Is this number here smaller than the top of the min stack, okay? Right? And it's not, right? Because 4 is not less than 2. So what do we do in that case? We just add the value that is at the top of the min stack, right? Because again, when we have this here, right, our min stack, our minimum value should be 2, right? Okay. Now let's say we had a smaller number, like a 1. Okay, we're gonna check this 1 against the top of the min stack. Okay, 1 is smaller than this 2 here, so we can actually add a 1 here. Okay. Now we're going to do a pop, which removes the element at the top of the stack, right? And so when we pop, right, when we pop here, we also want to pop here, okay? See how we just did that, right? We pop this, and then we pop this. Well, guess what? Our minimum value is still correct, right? So when we pop from, we have to pop from both, basically, okay? Now top is just asking us what's at the top of the stack, right? It's not asking us for the minimum or anything. So when we're checking top, we're just checking what's at the top of the stack. So it should be 4, right? Now, when we're checking get min, that's basically asking us what the top of the stack is for min stack, because that's the entire point of the stack, is to keep track of the minimum, right? So, yeah. I think this problem, honestly, it is a medium, and I will say it is a little bit difficult to come up with a solution on your own, but I'll say, like, actually understanding the implementation is actually very easy, in my opinion. And I think you will find it too. I mean, assuming you know how to work with stacks. And, you know, if you're following me on the Grind 75 list, we've done a problem already where we have to implement a stack. And I think, like, implement a stack using a queue, implement a queue using a stack, or stuff like that. So we should be kind of familiar how to implement this stuff. This one is just the tricky part, which is, how do we even handle that? And the trick is to use 2 stacks, right? Although I think on the previous stack problem, on the Grind 75, we had to use 2 stacks also. So you should be a little bit familiar with just using 2 stacks. But I mean, it's not relevant to this problem really, because this problem is a little bit different, but I just point that out. So let's create a stack. We'll just call it stack, right? And we'll create another one, and we'll just call it minimum stack, okay? Min stack, okay? Now the push here, remember what I said, right? we're checking this number with the top of the stack. But there is an edge case we need to handle, which is if this is we're not going to do any checking between the values if this is empty, right? Because if this is empty, whatever we append to the push, we do it to both, obviously, right? Because there's nothing to check against. Okay, so that's what we need to do. So we're going to say, first of all, we can append it to the stack, the first stack, right? Because this one order doesn't matter, because we're not tracking the minimum in this particular stack, right? So we're gonna say self.stack.append value. Okay. Now for the min stack, that's where this comes in handy. So we're gonna say if not self.min stack. So if min stack is empty, then we can just basically do the appending. Okay. So we're gonna say self.minstack.append val. Now this else statement is basically saying min stack has something in it already. So this is where we have to do the checking, right? So we're going to basically check whatever we're appending, right? Whatever we're appending, which would be like val, right? We're checking this, what we're appending, versus what's at the top of the min stack already, because it already has something in it if we're in this else statement, okay? So in that case, we're gonna say val is equal to the minimum between the val and whatever's at the top of the min stack. So we're gonna say, whoops, we have to do self.minstack and get whatever's at the top of the min stack. Okay. And then we do self.minstack.append val. That should make sense though, right? Because what we're basically doing is, okay, we're checking this for, right? We're checking this for against this one. Which one's smaller? The one. So we just add a one, right? So we maintain whichever we maintain and keep track of what the minimum is in our stack. Okay. Now let's say we add like a I don't know, like a 0 or something. Okay. Well then we would do, okay, what is the minimum between this 0 and this 1? The 0 is the new minimum, right? So the 0 would get added. Okay. So you can see how this is just basically the stack, and then this is the stack that's just maintaining and keeping track of which one's the minimum in our actual stack. Okay, but we need 2 stacks to do it, because again, we need to do this in O of 1 time complexity, right? Now the pop is, remember what I told you, right? With the pop, we need to pop from both, right? So we're gonna do self.stack.pop, self.minstack.pop, right? At the top here, we're just returning the top of the actual stack, right? So we're gonna say stack.name, because again, we don't care about the minimum or anything. We're just getting what's at the top of the stack, right? What's the last element we added? So we do self.stack -1 to get the top of the stack, right? Now here is the get min. Now that's kind of the point of having this stack here, is when we want to get the minimum, we just check the top of min stack, right? And we should get whatever the minimum is in this. Okay. So here we just do return self.minstack -1. Okay, and that's it. Right? Right? That's it. So I think this solution's easy to understand, as well as the implementation is pretty easy to understand. It's just it is a little tricky to come up with on your own though. I will give you that. Like knowing that you could use 2 stacks and use one of them to keep track of the minimum and the other one just operates like a normal stack, right? It is a little tricky. So it's okay if you didn't get it, but I do think the solution should make sense. It's fairly simple. Before I end the video, I want to correct myself. So I did say that you can't do this using any other way. You have to use 2 stacks. I think that's not actually true. I think you can use 1 stack using like a tuple, right? Where basically when you insert into the stack, you insert the value that you're actually pushing onto the stack. And also you keep track of another value, which is the minimum seen so far. So I think you can solve this problem using 1 stack. The reason I was saying that you can only solve this with 2 stacks is I think that like 1 stack approach is actually not that common. Like either one is fine. I don't think there's a right or wrong answer, because this problem description doesn't state that you know, you can only use one or the other, but obviously use a little bit more space if you use another stack, but it's really not a big deal. But if you're in an interview or something and they want you to use 1 stack, that's how you would do it. You would like how you at insertion you would add the value, but also you would add another value as like a pair, and the second value would be basically the minimum value you've seen so far. So that's how you could do it with one stack also. You can implement that if you want. I'm only going to cover this approach with two stacks because it's more common, a more common solution to this problem. I think it's a little bit more straightforward too, but yeah. Anyways, I'll see you in the next one. Peace out.